As we worked our way through the previous lessons, you may have wondered, well, what happens if there is a fraction or rational number in an exponent? Is that even possible? It very well is possible, and it happens all the time. So much so that there is a special definition and symbology associated with rational exponents that we'll cover in another video. As usual, we'll come up with a definition for ourselves by utilizing other rules we have learned. Let's start with 25 raised to the 1/2 power. Our first assumption would be to simply divide 25 by 2, leaving us with 12.5. But not only is that completely wrong, it's not ideal either. Let's look closely and analyze what we are working with, and ignore the rational exponent for the moment. What kind of number is 25? Does it look familiar? It should. It's a product of an exponential number. That exponential number is 5 squared. Since 25 equals 5 squared, we can replace that into our rational exponential number. 25 to the 1/2 power equals 5 squared to the 1/2 power. Now look at what we have, something that we were introduced to last lesson, powers of exponents. We should know how to do this. Using the power rule, we have 5 to the 2 times 1/2 power, which equals 5 to the 2 over 2, which simply equals 5. Look at what happened. We had a squared number being raised to the 1/2 power. Then the 2 powers canceled out. This is what we call a square root, because we are going to the root of our squared number. The square root of 25 is 5. Let's look at one more. How about 27 to the 1/3 power? Notice that 27 equals 3 cubed. We plug in the 3 cubed and end up with 3 cubed to the 1/3 power, which equals 3 to the 3 over 3, which equals just simply 3. Once again, the powers canceled out. This here is called a cube root because we are going to the root of our cubed number. The cube root of 27 is 3. Let's write our definition for what we have found. Definition of b to the 1 over n. For all b greater than or equal to 0 and all real numbers n, b to the n to the 1 over n equals b. This states that as long as our base b is non-negative, if our base is raised to a rational power whose numerator is 1 and denominator is equal to the root of our base, then the root and rational exponent cancels out, leaving the base. The reason for a non-negative base will be expressed in the final chapter of this unit. Let's work a few examples. Number 1, 49 to the 1/2 power. Here we have an example similar to the one in our lesson. We first recognize that 49 is the square of 7. Plugging that in, we have 7 squared to the 1/2 power, which equals 7 to the 2 over 2, which equals 7. Number 2, negative 16 to the 1/2 power. A very important note needs to be made here. We know that a square is made when we multiply a number to itself. In this example here, we have a negative number. Note, no two numbers multiplied to itself can yield a negative number. It is for this reason that we have stated that our base must be non-negative. Negative square roots are non-existent. Such roots will be covered briefly in the last chapter of this unit. We need to notice that our exponent does not affect our negative sign, so we must remember to leave it alone because it is not part of the base. our expression can be rewritten as -1 times 16 to the 1/2 power. We know that 16 is the square of 4, so we plug that in and end up with -1 times 4 squared to the 1/2 power, which equals -4 to the 2/2, which equals -4. Number 3, 1/32 to the 1/5 power. We work rational numbers the same way we would if the exponent was a whole number. We simply apply the rational exponent to both parts of the rational number. But since our numerator is 1, we can ignore it because 1 raised to any power is 1. Recognize that 32 is the 5th root of 2. So we plug it in and get 1/2 to the 5th power to the 1/5 power, which equals 1/2. Number 4, 25/81 raised to the -1/2 power. Now we have a negative rational exponent. Remember, we can always pull a number out of an exponent just like a normal number. We're going to factor out the -1. This gives us 25/81 raised to the -1 times 1/2 power. Now that we have the -1 out, we can go ahead and use the negative rule for exponents and take our inverse, giving us 81/25 raised to the 1/2 power. We now apply our exponent to both the numerator and denominator by the power rule. This gives us 81 to the 1/2 power over 25 to the 1/2 power. Recognizing the roots in our expression, we'll rewrite and simplify. 9 squared to the 1/2 power over 5 squared to the 1/2 power, which equals 9/5. Number 5, 64 to the 1/3 power divided by 36, all raised to the 1/2 power. Finally, we have nested rational exponents. We can do these one of two ways. We're going to work through both here. First way, we can straightway use the power rule for exponents and just multiply our exponent across the fraction. This will give us 64 to the 1/3 times 2 divided by 36 to the 1/2. Simplifying the numerator and finding our root in the denominator brings us to 64 to the 1/6 power divided by 6 squared to the 1/2 power. A 6th root might seem daunting, but notice that our base is an exponential number. Exponentials are based on multiples of 2. Simplifying our exponent, we have 2 to the 6th power to the 1/6 divided by 6, which equals 2/6, or 1/3. This is why simplifying is very important. A very complicated expression may just so happen to be a very simple number. Let's use the other format to simplify this expression. Noticing that our expression is nested, we could have just simplified the inner exponent first. Our expression then becomes 4/36 to the 1/2 power. Large numbers can be hard to work with at times, but if we recognize our roots, our work in math becomes drastically easier. 64 not only is the 6th root of 2, but it's also the 3rd root of 4. So numbers are proven to have multiple roots. Using the power rule now on what we have left, we get 2 squared to the 1/2 power over 6 squared to the 1/2 power, which equals 1/3. Thus, we have the same answer. That's all for this lesson. In the next part to rational exponents, we'll work with rational exponents that are slightly more difficult, but work in just the same way that we have worked with these.